Pi is surely the most famous non-integer. People from all walks of life are at least vaguely aware of pi. And what do you think is the one thing that everybody knows about pi? In the past, I might have said the one thing is that pi has something to do with circles.
But honestly, so much of the iconography of pi that makes it onto posters and merchandise and into the public consciousness has to do with its digits, nothing to do with circles.
I think the one thing everybody knows about pi is that it's irrational. Or, as a layman might describe it, it goes on forever. We can't compute it. We can't write it down. So then, explain this. A comment from r/learnmath saying pi is uncomputable, but it has 52 downvotes. Why? To explain the booing that Impressive-Mud5074 got, we need to know what computable actually means. Normal people might say, yeah, I know pi, it's that uncomputable number, don't even calculators have to approximate it? Your TI-84 Plus, for example, doesn't use the Platonic pure and perfect pi, but rather uses only 13 digits after the decimal. But when math nerds say computable or uncomputable, they mean something very specific. Once we understand that, we can better understand the extremist position that this commenter is actually taking. Yes, even math has extremists, and if you want to amass downvotes on math subreddits, there's hardly a tactic more effective than being a pea in a pod with this guy. So then let's get on with the explanation and the all-important context. Then if you think you need to, you can go downvote Impressive-Mud5074 too and show him what for. When he says that pi is uncomputable, he doesn't mean the same thing that a mathematician typically means. In 1936, Alan Turing introduced computable numbers with this informal definition: the real numbers whose expressions as a decimal are calculable by finite means. So then pi is uncomputable, since its decimal expansion is infinite and non-repeating. There's no finite process to simply produce the decimal expansion of pi. But that's not exactly what Turing meant. His definition in full detail involves computable sequences and A-machines, which would later be dubbed Turing machines. The modern definition, which is mostly equivalent, is that a number is computable if there is a finite terminating algorithm which can calculate it to any desired precision. Finite and terminating are the key words here. What would a finite algorithm for pi look like? Well, we could just use any of the well-known infinite series for pi. These sums are, in theory, infinite, but the instructions for carrying them out as far as we need are finite. The instructions are right there. We can add up as many of the terms as we'd like or need, and the algorithm will stop once it's added our desired number of terms. At this point, a counterexample may shed light on this idea. If pi actually is computable because we can approach it with an infinite series, then what the heck is an uncomputable number? We'll save that for the end, but for now, the point is, pi absolutely is computable. By Turing's definition, which we didn't go fully into, and by the modern definition. But what about Impressive-Mud5074's definition? I suppose we need to look at the argument. The thread Mud commented on basically asked for novel examples of uncomputable functions. They're like uncomputable numbers, but they're functions. Mud's irrelevant response simply said, pi is uncomputable. And then some incredibly optimistic people attempted to reason with him. OP replies and explains that pi is computable, and commends Mud on his boldness for answering a question without looking up anything beforehand. In response to the correction, Mud explains what a transcendental number is. OP says that's not what computable means. Mud says, yes it is, and then he gives a hint towards what he's actually talking about. He says you can approach pi, but not compute it. It's apparent that his issue with pi is that it's irrational, and its decimal expansion can't be exactly computed in finite time. Then MA4R joins the fight and says, please, for the sake of God, just look up what computable functions mean before you reply. Mud politely declines and provides a link to the Wikipedia page on ultrafinitism. This is like if I was debating you on the shape of the Earth. You say, I don't think you understand. The Earth is a sphere. Watch a video of a ship sailing towards the horizon. And in response, I link you the Wikipedia page on idiots. But yes, it's clear Mud has a philosophical contention with this discussion that prevents him from even engaging with this question of computability. He's an ultrafinitist. It sounds cool, but in math circles, this title is a scarlet letter. And you might think, oh, come on, scarlet letter, surely our beloved math people are polite and open. All ultrafinitists are idiots. So what the heck is ultrafinitism, and why is this actual perspective about mathematics so unceremoniously dismissed on r/learnmathematics? In short, ultrafinitists are not so quick to permit arbitrarily large numbers simply because our symbols are powerful enough to denote them. Just as a hypocrite speaks oaths and writes pledges, what meaning does it have if these promises remain empty words next to evil deeds? And what about 2 to the power of 100? This number is so great that in seconds it represents tens of quintillions of millenniums. Is it meaningful to say such a number exists? Ultrafinitists believe we have to draw a line somewhere. There's a point at which numbers grow so high and become so large as to cast shadows of doubt over gods. This is in contrast to a finitist who's willing to permit a whole number of any extraordinary size, but to consider an infinite object like the set of whole numbers is strictly forbidden. But our humble pi is plankton in a tsunami compared to infinity. So on what grounds would Mud oppose this number? Well, in his Arithmetica Integra back in 1544, German monk and mathematician Michael Stiefel put it well when he said, other considerations compel us to deny that irrational numbers are numbers at all. To wit, when we seek to give them a decimal representation, we find that they flee away perpetually, so that not one of them can be apprehended precisely in itself. Now, that cannot be called a true number, which is of such a nature that it lacks precision. Therefore, just as an infinite number is not a number, so an irrational number is not a true number, but lies hidden in a kind of cloud of infinity. Wow. There is clearly some fragment of infinity within an irrational like pi. A fragment that may be enough to enter pi among an ultrafinitist's lists of numerical cryptids. But again, it is a finite number, and it can be computed via a finite algorithm. So really, why would an ultrafinitist, or Mud specifically, deny the existence of pi? Or would they? Well, in another comment chain on the same thread, Mud pokes further and receives more free tutoring from the LearnMath subreddit. He links to ultrafinitism and says very large numbers are uncomputable, which colloquially may sound true because of obvious physical limitations of computer memory and available time, but we're talking about the mathematical notion of computability. Now, the formal definition does appeal to a model of computation in order to formalize the meaning of algorithm. The most standard such model being the aforementioned Turing machine. This model is defined to run on an infinite tape and can, depending on the program and input, run perpetually and never halt. All of this to say that whole numbers of any extraordinary size requiring any inconceivable amounts of computer runtime to print as a binary string are still, by definition, computable. Because simply put, the size of a number is not a relevant fact for the models of computation that are part of the definition of computability. Imagine an epic username asks Mud, with the prevalence of people here disagreeing with you, why do you claim your point and definition hold? Mud says it's because logic says he's right. Imagine an epic username replies, it's not a matter of logic. Hey, don't bleep, I didn't say anything. It's not a matter of logic, but definitions. What you're trying to explain is an irrational number, not uncomputable. Though remember that uncomputable numbers are not the topic of the thread either. The topic is uncomputable functions that aren't derivative of the halting problem. But the topic of this video is Impressive-Mud5074, so let's continue. Mud specifies what he means by computable, that it finishes computing, and draws a comparison to the halting problem, the problem of determining if a program will halt or run forever on a given input. He basically argues that if we can say pi exists simply because we can run algorithms for arbitrarily many steps to achieve a desired level of precision, then we might as well say we can simply stop a program at any arbitrary point we like, and so all programs halt, which contradicts Turing's landmark 1936 paper that proved the halting problem is undecidable. Whether or not a program will run on an input should be inherent to the program and the input, if there is one. An external source can't arbitrarily decide to stop the pair from running and thusly conclude that the program halts. And Mud views pi similarly as having an inherent fragment of infinity. To say pi exists because we can stop an infinite procedure at any point we like for a workable approximation, in Mud's view, evades the central issue entirely, just as stopping a program manually evades the question of whether it would ever halt naturally. But imagine an epic username deftly reposts Mud, explaining the key difference. To know if a program input pair halts, the computation has to be carried out, the program has to run. But for the series that converge to pi, the output is already known. The only question is how far out you want to take the computation. But this still ignores Mud's philosophical issue with the number. We can stop our sum somewhere for an approximation, but we know that the series does not halt. They are, by their definition, infinite. Imagine an epic username attempts to reassert the definition of computable, emphasizing the arbitrary precision, but honestly, Mud cooks him. I choose 100% precision as the arbitrary amount. Do that, thanks. Of course, in the definitions, this arbitrary precision refers to an arbitrarily small positive error, which means that zero error, or 100% precision, is not covered by the definition. But it is a pretty funny response. They continue to go back and forth. Imagine an epic username says, it's hard to convince a smart person, impossible to do so for an idiot. Mud replies, I'm trying as hard as I can to convince you. Sorry. Suffice to say, no, Mud definitely does not believe in pi. Because even though it is finite and computable by our definition, he's concerned with the actual process of computation. And obviously an ultra-finitist is not going to admit an infinite process to define a number. Or at least that's what Mud thinks. But what about ultra-finitists in general? I suspect they'd all agree with Mud on some level, but it's difficult to say precisely. I'm no expert on ultrafinitism, and the belief is fringe enough and not quite well developed enough to have a universally agreed upon formal foundation by its proponents. And that's part of why it's typically dismissed so quickly. For most mathematicians, there's already a pretty satisfactory foundation for maths, which does permit forms of infinity. No need to reinvent the wheel for a more constricted system that's less developed. But for sake of example, we might as well look at another ultra-finitist. Among the most famous is certainly Doron Zielberger. I saw him give a talk some time ago, but he had a thick accent and I couldn't understand a word. but thankfully he has a lot of written work. And in his essay, Real Analysis is a Degenerate Case of Discrete Analysis, he says it's utter nonsense to say square root of 2 is irrational, and he would presumably think the same of pi. Indeed, to call it irrational presupposes that it exists. Throughout this essay, Zielberger is discussing the true nature of our mathematical universe. We often discuss the real number line, but Zielberger asks us to consider the real number line, which he says is neither real nor a line. His conception of the number system has some biggest number, a massive unspecified prime p. Additionally, between the whole numbers isn't a smooth continuum of rationals and irrationals, but rather a discrete set of values that are very close together as determined by a small unspecified mesh size h. And since this conception of the real numbers only admits multiples of the small rational number h, it certainly doesn't admit pi as we know it. And Zielberger doesn't view this exactly as a line, but as a necklace or loop, upon which something called modular arithmetic applies, but that's not relevant to the pi discussion. At the end of the day, I hope you come away from all this with an understanding of the disagreement on display. Unfortunately, Mud doesn't give a steel man of the ultrafinitist position. He doesn't engage with any depth or precision, preferring to proffer links and witticisms. It's as if he was the one with the prevailing opinion, and was simply brushing off others who are interrupting a thrilling ultrafinitist discourse. But make no mistake, at least on a surface level, there are many smart people who agree with Mud, and have written many interesting essays and arguments about the ultrafinitist position. But one loose end remains, which is the other side of uncomputable numbers. We've been talking about Mud and the ultrafinitists, and they think a bunch of numbers are uncomputable, the really big ones and the really specific ones. But considering the actually common definition of computable number, it is rather difficult to think up a counterexample. Usually algorithms are how we can deal with the messier numbers, so if an uncomputable number can't be approached by an algorithm, how could we even specify it? How do we set our fingers upon the unreachable? One answer to that question is as unsatisfying as it is astounding. First, it's important to know there are many more real numbers than there are whole numbers. We can count the whole numbers, 1, 2, what's next? 3. That's right, good boy. Accordingly, the whole numbers are said to be countably infinite. But the real numbers, which can't be counted or listed in this fashion, comprise a much greater infinity. Any attempt at listing all the real numbers is easily shown to be incomplete by Cantor's diagonalization argument. All of this to say, if we have a countable list of numbers, then practically every single number in existence isn't in the list. Countable infinity is tiny. Returning to the question at hand, how can we entertain the existence of uncomputable numbers if we can't even name one? If by definition an algorithm can't even approach one? Well, certainly any computable number, since it can be defined by a finite terminating algorithm, can also be described in our natural language by describing the algorithm. Like pi is 4 times the limit of the alternating sum of the reciprocals of odd numbers. Now, here's the crazy part. How many English language descriptions of numbers are there? The answer is that very tiny countable infinity. This symbol for it is pronounced aleph null. To show this, just take our 26-letter alphabet, throw in some punctuation symbols, and enforce this order. Then certainly the list of strings is countably infinite. There are the 1-character strings, which can be ordered in their natural way, then the 2-character strings, all the 3-character strings, and so on, all ordered in their lexicographic or dictionary ordering. Considering all possible strings of these characters, most of them will be nonsense. But some of them will be English sentences. And some of those English sentences will be precise descriptions of particular numbers. Now, certainly, the list would contain precise descriptions of every computable number, since somewhere in the list would be a description of the appropriate algorithm. But how many of the numbers would the list miss? Well, since the list is countable, we would be missing basically all of them. And every one of those, almost every single number in the world, that we missed is uncomputable. That is disturbing. However, our list of English strings will also contain some descriptions of uncomputable numbers. Although we've accepted for this argument that a finite terminating algorithm can be turned into natural language, the converse is certainly not true. So let's finish with that, a natural language description of an uncomputable number, which is necessarily not something that could be turned into an algorithm for precise computation. And since it's come up a couple of times now, let's build the number from the halting problem. I will attempt to do this as quickly as possible, and thus avoid going into a detailed description of Turing machines, or any rigorous computation model. Beneath the surface, computer data is binary, zeros and ones, which are called bits. This is the language comprehensible to electronics that are built from on-off transistors. There is electric current, or there isn't. An obvious consequence of this is that, if desired, we could encode any and every computer program as a finite string of bits, as well as every input that a program might take. So here in this table, we have every possible program and every possible input. And note that we can do this because finite bit sequences are countable and can be ordered. We can just order them by their lengths, and then within each length, order them by the size of the number the bit sequence represents. So if programs and inputs can be bit sequences, then we can order them. So again, here we have every possible program with every possible input. Some programs will run fine with no input. Some programs may not be able to take a particular input and would halt immediately. And certainly, some program input pairs will run forever and never halt. Regardless, now that we have every possible program input pair, we can enumerate them, or put them in order. The ordering follows this simple zigzag pattern along the diagonals. So this theoretical collection of every possible program and input pair is countable. There's a first, second, third, fourth, fifth, and so on. Now, consider this indicator function xn. We have an ordered list of every possible program input pair, so how xn works is it equals 1 if the nth program input pair halts, and 0 if it doesn't halt. And now, here's our guy. This number is surely uncomputable, for if there was an algorithm to compute it, that algorithm would have to solve the halting problem for every program input pair. But we know the halting problem is undecidable. It's perhaps unsurprising that our descriptions of uncomputable numbers seem a bit more like thought experiments. Such is the abstract nature of tangling with infinity. Aristotle entertained infinity from two perspectives, actual and potential. Describing potential infinity, he wrote, "For generally, the infinite has this mode of existence. One thing is always being taken after another, and each thing that is taken is always finite, but always different. Actual infinity, on the other hand, he deemed complete, definite, and impossible. Perhaps it's our hubris, and not our sense, that allows us to speak the heavens themselves into existence with the axiom of infinity. Perhaps, in mud, we should find a humble hero, content in his finite world and his very finite intellect. If the ultrafinitists are wrong, we ought to go on enjoying our toy and dancing with infinities in Cantor's paradise. But if they are right, as Zielberger says, what is completely meaningless is any kind of infinite, actual or potential. If they are right, then it's all the more important that we dance with what little finite time we have left before we are expelled as fools from paradise.